Dr. Chris Willacy received his MSc in 1991 in Computing Earth Sciences from Kiel University and a PhD in 1996 in Geophysics from Royal Holloway, University of London. He joined GX Technology from 1996 to 2006, where he specialized in applying depth imaging and velocity modeling building techniques across the globe. This led to the development of several large multi-client projects culminating in the first regional basin span surveys. Since joining Shell in 2006, he has worked for the ENP in a variety of geophysical technical management roles like SIPMAP, global seismic processing, hi-fi R&D in Houston, Amsterdam and London. He has successfully led several global task forces, microseismic event detection, deblending, energy transition, and he is currently a principal geophysicist in the Geophysics East UPV organization and SME for storage geophysics. His research interests include refraction-based imaging methods, signal processing, velocity model building, and microseismic event location. Chris, the floor is yours.
Thank you very much. Can you hear me okay? Yeah, we're all working. Well, glad to see you all, and it's been great to talk to a lot of you over the last few days. I'm here to talk to you about hydrogen storage monitoring. There's a small caveat to that, though, is we haven't actually done any. However, we're one of the few companies that has successfully stored CO2 in the subsurface. So what I'm going to talk to you about today is a little bit about some of the experience with CO2 storage and how we're taking that forward to better understand how we can create hydrogen stores in the subsurface. Just the Shell legal cautionary note, which basically says don't believe a word I'm about to tell you. So, but you will, yeah. So I'm just going to very briefly cover some of the challenges and risks of hydrogen storage. I think this has been covered a lot in the last few days, so I won't go into that in too much detail. But I want to talk to you about how we actually manage subsurface storage and how we actually monitor for that and how we verify that we have containment and conformance in the subsurface. We'll look at a few of the seismic monitoring technologies which we've successfully applied for CO2, and then we'll try to understand the detectability going forward for hydrogen storage, and hopefully I'll have time to show you a little example of some fluid substitution modeling where we're actually comparing CO2 with hydrogen in a subsurface reservoir. Okay, so we've heard a lot over the last few days of the applications for hydrogen storage, and the two main ones that have been discussed are around storage in salt caverns and in porous reservoirs. Now, I think it's clear that whilst the storage in salt caverns has been clearly demonstrated to work operationally, we have to do this at mass scale. So we're talking of significant increase in caverns in salt masses around the world, and that probably brings with it additional associated risks. One of the key issues I think that has been also highlighted is salt is not homogeneous. So it varies considerably chemically. It includes inclusions. We have gas inclusions in salt, for example. We have shear zones. We have encased sediment. And these all potentially are risks for storage caverns. We may have leakage pathways in salt domes where we may get loss of containment. The geomechanics was ably discussed by one of the previous presenters, but obviously the cyclic nature of repeated injection of hydrogen and withdrawal are potential challenges. On the porous reservoir side, we have seal integrity. We have probably the big elephant in the room, which is microseismicity, which we haven't heard an awful lot about over the last few days. But of course, microseismicity, wherever we're putting fluids and gases in the subsurface, we are more than likely to get microseismicity, and we have to deal with that appropriately. This obviously impacts societal acceptance for hydrogen storage. And of course, there's a lot, again, around the geomechanics, but also a bit of politics here, particularly around if we're using stores for enhanced oil recovery or enhanced gas recovery. So it's a sensitive topic, which I'm not really going to get into, but obviously that comes into play. So I'm going to focus more on porous reservoirs here, but I just want to say that at Shell we've put together quite a large team and program that's working very hard to establish hydrogen monitoring as a safe and viable part of our business. And you can see the key elements of that program here. So we're looking at hydrogen loss and contamination, reservoir performance capacity, wells facilities, storage integrity, the monitoring and verification, and of course developing that aspect of the business and also the public acceptance. And this program is ably run by Karen DeBorst, who's in the audience here, that many of you know, who is waving right now. So if you don't know her, you can see her. And I'm sure she'll be happy to answer more questions on the program overall in the coffee break. So I've highlighted here the monitoring verification. So that's the one I focus on as a geophysicist. But how do we really go about monitoring stores in the subsurface? So for this, we rely on what we refer to as measurement, monitoring, verification, or MMV. So if you have not heard of MMV before, it is essentially a risk-based approach to monitoring stores, where you take into account all the risks associated with your storage site and your activity. And typically this is laid out in the form of a bow tie, which you see upper right here, where you identify the potential threat. So it could be loss of containment. And then you look at all of the triggers that may lead up to that, and you try to put barriers in place to prevent those threats from escalating. If, however, that you achieve the top event, so let's say you had loss of containment, then again you would have a whole series of barriers in place to try and reduce the impact of that top event. So this risk-based approach goes into the detailed planning for subsurface storage. It has been developed largely at Shell around CO2 storage sites, but we're adapting the MMV planning for future hydrogen storage. And again, this is very important for establishing a license to operate for these fields. As an example of an MMV plan, I refer you to one here that we're showing from our Quest CO2 storage facility, which is located in Alberta in Canada. And the original MMV plan is shown just top left here. This is the original plan that was put together in 2015 here, just showing a summary of it. The key points to really highlight here are the fact that it's multi-domainal. So it's covering the atmosphere, the biosphere, the hydrosphere, and the geosphere. And within the geosphere, you're monitoring essentially from the surface with typically surface-based seismic acquisition, and then covering the wells, whether it be dedicated monitoring wells or the actual injection wells themselves. And in each of these areas, you're also covering pre-injection, injection, and closure phases. So it's not just once you've started injecting gas into the subsurface. Now, at the moment, we haven't actually closed anything. That is still all in development. But we do have protocols in place for what we would do in a closure phase. And obviously for hydrogen, we are very early in the planning. But MMV should be done early. It's not something that should be done late. You really have to think about this in order to successfully operate. Now, one of the things that does happen, though, is that over a period of time, of course, once you do start to operate your field, you actually start to get data coming back. And that allows you then to history match with your predictive models to see how well things are behaving in the subsurface. And then the MMV plan is periodically updated. So here you can see the 2020 version, compare it with the 2015. We still have the same domains that we cover, but the range and type of technologies may have changed based on experience. And in the case of Quest facility, we found that our initial plan was probably a little bit over the top, so we had more technologies than we probably needed, but we also wanted to gain experience with operating this CO2 site. But with time and data, that allowed us to refine the MMV plan and get something that was a bit more fit for purpose, but also more cost effective. So some of the main things we're looking at regard to monitoring revolve around 4D seismic time-lapse monitoring, which is probably the main type of monitoring that we'd use for future hydrogen stores. And there are a few key elements that we need for this. The obviously one at the left here is, in order for it to work, we need a sufficient fluid response in the subsurface. So when I refer to fluid, obviously a supercritical fluid or gas type of response. And we need that in order for this technology to work. The second item we need is we need at least a cat, right? Or at least a cat you can see. But this is really about resolution. We must have surveys that can resolve the targets that we're interested in. The repeatability of the surveys is critically important. So this is a 4D time-lapse type of monitoring, where we take a baseline before injection, and then we will repeat the survey at different times throughout the monitoring period. And we must be able to repeat that survey as exactly as possible in order to minimize potential noise sources between the base and the monitors. We also, of course, have noise inherently in the subsurface. It may be random or coherent, so we must design surveys such that we can see the things that we want to see in the subsurface. And of course, for hydrogen storage in porous media, this would be trying to visualize the plume itself. And then the timing of these monitors is important. So it's you have to put sufficient monitors in that we can see the evolution of the plume in order to answer the questions that we need to answer relative to the store, to make sure we do have conformance. It's no good doing this too late in the process or too early if there hasn't been enough storage of hydrogen, for example. So an example from, again, from the Quest site. This is showing you one of the applications, the key technologies that we do. So this is 4D time-lapse using distributed acoustic sensing. So distributed acoustic sensing, for those who are not familiar, this is an acoustic fiber that we cement behind the well casing. This is basically, we fire short bursts of laser light throughout the fiber optic cable, and the cable is very sensitive to any mechanical strain against the cable itself. So we actually measure the travel times of the laser pulses, and this essentially can be converted into an amplitude type response. So what we've done at Quest is we've used this DAS VSP type of monitoring. We have to create a solid baseline, of course. Before we do any injection, we have to understand what does the subsurface look like. So this is absolutely mandatory. And then over successive years, we've repeated that same survey. So here's one in 2017. So after we've started injection, and one in 2019. And then we actually will then look at the difference between these monitors and the baseline. And if everything's done exactly correctly, then what we should see is a 4D difference. And that's what you're seeing here on this image. This is a 4D difference between the baseline and one of the later monitors, probably 2019 here. And what you do see is you do get a little bit of residual in here. It's hard to get it completely exactly right. But what you see is quite a nice, clear amplitude anomaly of the CO2 plume that's been injected. In the case of the Quest site, we're around about 7 million tons of CO2 that have been stored to date, over around about 1 million tons per year. And you can see the evolution of the plume from that CO2 on this map that's shown. And it starts off fairly symmetric, but what we found with experience that it became slightly elongated towards its eastern side, and it's largely due to the permeability within the reservoir. Now, another aspect of that we're actually investigating at Shell is, can we take that technology I've just shown you and apply it readily for hydrogen? Likely we can, but there are things that you need to be a little bit careful of. And one of them is to do with optical aging of the fiber optic cable. So glass is potentially sensitive to contamination of hydrogen. And there are essentially two parts to this, right? So if you introduce hydrogen to the fiber optic cable over relatively short timescales, you actually see attenuation building up within the fiber optic itself. So you can see on this display here that we actually have some absorption of the hydrogen within the actual fiber, and it causes attenuation of the light pulses that go through it. So effectively what this would mean would be that you would get reduced amplitude coming back, reduced frequency from your seismic. So this becomes quite a challenge. Now, on the short periods, if we diffuse the hydrogen, then typically this is reversible and we get back our perfect optical properties. However, over extended periods of contamination, we will get alteration of the fiber itself, and then we get more permanent damaging. And this is referred to darkening. So essentially the fiber will go dark. And of course, for a receiver essentially that relies on light transmission, that's fundamentally a problem. Now, this can be overcome. There's a number of coatings and shieldings that are put around the fiber to protect them. And this is something that my colleague Claudio Filomena, who's waving at you right now, is working on at Shell. So if you want to know more about this phenomenon, I'm sure he'll be glad to talk to you in the coffee break. So we mentioned microseismic being the elephant in the room, and here's an example I'm showing you from, again, from our CO2 store, where we do have microseismic activity. Now this is typically very low magnitude, so low in fact that you wouldn't by any means be able to detect this physically yourself at the surface. So you don't see any physical manifestation of these events, you don't feel the ground shaking or anything like that. So they're very low magnitude and typically only recorded with very sensitive instruments like geophones. However, they do exist, and they exist largely because of the varying changes in pressure in the subsurface, and many of the reservoirs where we're hoping to inject CO2 or hydrogen contain faults. And a lot of these faults may be in close to a critical state. So it doesn't take an awful lot of extra pressure to cause those faults to slip. So this is something that we've had quite a lot of experience with, microseismicity. We believe that you're going to get this on probably most sites globally. There are very, very few subsurface stores that don't actually show any microseismicity. So likely this is the problem you're going to encounter. Has to be overcome. We have to monitor it in the subsurface. And of course, we have to make sure that our operations are at sufficient levels not to cause escalation of this, that we see these numbers getting higher and higher. Okay, the other key technologies that we're using, frankly, we are very data poor when it comes to hydrogen, and I think that's also been mentioned. We simply don't have enough data to work with. So in the absence of data, we create data. So this is showing you some quite sophisticated numerical modeling that we do. So we take a fluid response in the subsurface for hydrogen. We create a 4D model of what a plume would look like. And then we create an acquisition, seismic acquisition over that, and then generate the subsurface image, as you can see here in this little example. This one's actually been taken from a current storage site onshore Netherlands that we synthetically would create hydrogen injection into, and then we monitor the 4D effect. So here you can see the map the amplitude map at the top of the reservoir. So this is top Rotliegend level. And then you can see the plume that we've artificially inserted at a synthetic injector. Now, what we want to do is to image that plume sufficiently well with our acquisition methods, but we also want to invert the data that we get. So we use seismic inversion to try and recover the subsurface properties of that plume. In this particular case, we have an example which we refer to as the bullseye model, which really has artificial boundaries for saturation levels. So we have a 100%, 50%, 25% horizontal layering within this plume. We invert for that to try and recover the saturation levels that you see here. And overall, the recovery is quite good, but the absolute levels are a bit off. And that's because we're dealing here with an acoustic inversion. So you have to go to increasingly more and more sophisticated numerical solutions to get more accuracy here. So we're currently running elastic simulations, which typically do a little bit better job of that. And obviously what we want to see is, do we recover the model that we build in the first place? I'm just going to run through a few slides now on some of the rock physics models. So this is particularly important for understanding what is the response to monitoring in the subsurface. Many of you will probably know what fluid substitution is. For those that don't, I'll just show the cartoons here, the short version. Essentially, we have a reservoir rock that has some pore fill. Let's say it's a saline aquifer, so we're full of brine here. And then we have a rock matrix. We estimate what the bulk modulus of this is, which is essentially the ability, or sorry, the resistance to the interaction of pressure and the change in the volumetric volume of a particular sample here to that external pressure. So it's the resistance here to check that volume change. We strip out the fluids, so we assume we now have a dry rock. We repeat the bulk modulus estimation for that. We then substitute this original fluid with another one. So let's say this is CO2, or let's say it's hydrogen. And then we put that fluid back in the rock, and we then look at the overall fluid response. So this is the famous Gassman fluid substitution equation, which relates the saturated incompressibility of the rock with its rock frame, mineralogy, and porosity. From this, we know the relationship with the density and the velocity of the rock, and then we can actually derive the velocity and density changes as a result of this substitution. And that's basically what the seismic is responding to. It's this change. Okay. So, however, this type of modeling, which has been used for decades, has some caveats with it. And one of them is that it assumes a fairly uniform distribution in the reservoir, where all the pores are in communication and you have an isotropic state of stress, which in reality is not going to happen. So this assumption is really not going to work out. And what you tend to likely get is more of a patchy type of response, where you have smaller and larger accumulations of the gas or fluid within the reservoir itself. This has a marked change on the elastic properties of the reservoir. So here we see the percentage of gas saturation that's being injected over a period of time with the velocity actually of the reservoir itself. And you can see that as we increase, let's say, the patchiness, which is more or less in this kind of this vector, this direction, we start to get less of a response, or more of a weaker 4D response to the actual the fluid substitution. Now, these are things that have to be overcome, and these are the things that we are researching. One of the problems with our current rock physics models, there's a bit of a difference between some of the theoretical models and the observations that we have in laboratory experiments. So you can hear some work by Falcon Suarez et al., where they're showing some results from core experiments, where they tend to get results that are showing significantly stiffer response than the traditional Gassman types of models. That's a bit of a problem. And to be honest with you, we don't seem to have really a consensus in the rock physics community on what is the way forward here. So if you know of any rock physics folks that you have in your organizations, please ask them to work on this problem, because we need more sophisticated models. We have spoken about the chemical and biological effects in the last few days, so I won't labor on this, but the main point, why would this be important from a seismic perspective? It may not be, but what you do see in the case of CO2 is we do have formation of carbonic acid, which can cause alteration of the rock frame itself. So we can get dissolution, precipitation, and cementation within the rock frame. So we're fundamentally changing the elastic properties of the reservoir with our injection. Will that have an effect at seismic scales? Possibly not, but these are things we do need to consider. On the hydrogen side, of course, we have the generation of H2S, so we have issues potentially with corrosion of instruments that we may put down the boreholes. And again, if this happens at a grand scale, then maybe we're seeing changes in the elastic response to a seismic wave. So to finish, I'll just show a couple of slides. This is showing you some of the modeling that we've done. So this case is an example from the Rotliegend reservoir, where we take typical Rotliegend parameters, and we're looking at just some basic fluid substitution here. So we start off with a rock that has 100% water fill, 0 hydrogen, and then we're going to reverse it. So we're 100% hydrogen here. And what you do see from these plots, we see the fluid response, the rock response. You see that the density, the horizontal axis here is increasing hydrogen saturation. As we keep on injecting, the density keeps going down, because we're putting lower density material and we're displacing water in this case. What you do see is it has a marked change on the velocity of the reservoir. So with just a few percent gas added, less than 5% for example, we have a significant change in the velocity. But over a period of time, this starts to increase for this particular scenario for Rotliegend. So this is fairly high temperature, 115 degrees Celsius, about 200 bars. So we're looking at about 2.5 kilometer scenario, so a deep reservoir. The main thing from a seismic monitoring response is this impedance change. So what you're seeing is what we would call typically a 4D softening of the reservoir. So we're getting a reduction in the impedance. So this is the product of density and velocity, and this is going down to a lower level. So these are levels that are readily, easily detectable with 4D seismic data. If we compare this with CO2 storage for the same sort of scenario, what is the difference between CO2 and hydrogen? Well, here we see we get, again, for less than 5%, very similar types of effects. So a reduction in the P wave velocity. Shear wave velocity doesn't change much. There's a little density change, but the shear rigidity is kept constant in fluid substitution. What we do see is we keep injecting higher and higher saturations, the density goes down. And of course, the impedance starts to go down. And what this actually shows is that hydrogen potentially is more visible to seismic than CO2 is. So you actually get a bigger 4D response as a result. So that is good news. The not so good news is the fact that this velocity starts to increase. And this puzzled us for a little while, but the reason why it increases is because you have to look at the calculation of velocity here. After a period of time, the compressibility remains, in the saturated rock, remains fairly constant, fairly level. And the shear rigidity, which is G here, also is fairly constant in this case. The only thing changes is the density. So the velocity actually starts to increase with increasing saturations. This effect seems to happen around about 200 bars. So for the deeper pressure reservoirs, we start to see this reversal. Now, why is this potentially a problem for monitoring is because some methodologies, like full waveform inversion, for example, are specifically looking at velocity changes for monitoring. And this basically suggests that for a rock that has no saturation versus one that has a high saturation, there may be very little velocity difference between the two. So that method isn't going to work. But what you do see is a constant change in density. So those technologies that rely fundamentally on density or resistivity, so for example electromagnetics, microgravity, may play more of an important role here for these types of injections. Okay, so final slide from me, and we'll get on to coffee. We repeat these experiments just to show you what happens in the case of depleted oil reservoir and depleted gas reservoirs. So the values that I've used for these simulations are, let's say, reasonably representative, right? So we've assumed that we've got a certain level of oil depletion, but we've got residual oil in the reservoir, and the same for gas. We've got a certain representative value of gas. And what you do see that for aquifers, the impedance change due to injection is very high. And this is, again, for a Rotliegend example, which is quite deep. If you go shallower, the response would be actually bigger. So this is going to be very, very easy to monitor with 4D data. But when you go to depleted reservoirs, you typically have much smaller voidage space. So you'll have likely some aquifer invasion after you've depleted the reservoir. You then inject your hydrogen into that. What you're going to displace? Well, we're not going to go to the bit where we're displacing the oil or the gas, right? Because that's the controversial bit. Let's say we displace the water. So this is what is happening in this simulation. We displace the water that's in that depleted reservoir, and you do get a response, even for a gas reservoir. However, that is much, much lower than you get for a saline example. And then you have to ask the question is, well, can I monitor this type of impedance change? It becomes very site-specific. Geology will play a big part. Obviously, the signal to noise you get from your surveys. So it really depends for these cases is the answer, right? We have to really look at these more to see how valuable they are from the monitoring perspective. Okay, so I think I'll leave that there. Just to point out, yes, we have storage is economically viable, we believe. There's a lot of technology I think we can transfer directly from our experience with CO2. But there are things, as I pointed out, that we do have to take a closer look at. M&V certainly allows us to try to de-risk these operations, and it's often mandatory for a regulator. So this is something that we have to embrace and take forward into hydrogen storage. We also have challenge. We're doing more work around salt caverns to have a closer look at that. Some of the things I spoke to you more specific about porous media, but if you actually had a leak out of a cavern, you're going to leak into the overburden, and some of the things that we've looked at with regard to detectability equally apply in that case. And finally, we have to basically put in the science here, because we cannot assume anything in this case. We have to make this a success for all. So I think I'll leave it there. And of course, there are many people at Shell that work on these things. So back to you.
Thank you very much. I think there's room for some questions. Yeah, and we'll go.
Hello, Arnaud Reveillère from Geostock. Thank you. Thanks a lot for the presentation. And I've got some conflicting opinions in my head after that, so I will share that here. It's not a coach, but in some ways, it's I find it very interesting that you looked at that and that you apply, for instance, 4D seismic to a hydrogen underground storage, and your analysis of the impedance difference you would see with these different gases in aquifers, depleted oil or gas fields, and it's very interesting that the CCS community and Shell, major companies, bringing this knowledge to underground storage. And on the other side, I'm also you're taking CCS as a basis for MMV, and so it's I think there are 27 injection projects starting with, let's say, Sniper 30 years, and not the natural gas storage, which is that has started first storage in depleted field in New York State 1915, I think, in Salt Cavern 1970. And actually in 600 operational sites today globally. And I think they don't use 4D seismic, and I think in this industry they probably never had the money to do that, and maybe some of them can confirm it. And and so I'm also thinking if we set the standard too high, I mean this hydrogen storage industry that is not even there. And it is much closer to the natural gas storage industry. It's been said by Hadid, by others, and that I've never seen 4D seismic in a natural gas storage. And maybe there are cost reasons. There are also maybe technical reasons. I see the interest. Salagner, I think, demonstrated the interest for tracking the plume and how it evolves, because you don't really know accumulated under these different layers. Not sure we've got that interest in a storage where there's a closed trap and it's moving in and out, and a well can just track and see whether the plume is here, because it's coming here and back again every year. So in some ways very interesting, and in the other ways I think we should also be cautious about what this industry will be able to afford. And of course we have to bring knowledge, and technology evolved like that from other fields. But we also have to be careful about that.
Yeah, if I can comment to your comment. Yeah, you bring up a good point. 4D seismic, typically, certainly surface seismic, is an expensive undertaking. So things like VSPs bring that cost down substantially. But why would you do this? Well, first of all, we want to understand what the 4D change is within the reservoir. Although we're modeling that significantly, I don't think we fully have that worked out yet. Again, as an operator of a field, you often have to prove, in this case, and we will have to prove with hydrogen, is that we have conformance and containment within the reservoir. Now, how do you do that? Do you do that with very lightweight monitoring? Possibly. Pressure gauges within wells would detect if we had a loss, for example. But they can be ambiguous as well, right? So often it comes down to, can we actually see the plume, as opposed to detect maybe the presence of the plume, which could be more of a challenge for very sparse types of monitoring solutions. So typically where we did with, I guess, with the Quest site is we started off more with the surface seismic, which for any typical storage site, we have to have a good baseline over an area that's bigger than the storage site. We have to know in that area that there are no anomalies to start with. Because if we inject anything into the subsurface and later we see potentially a change, then how would we prove to a regulator that it wasn't there before, or it was something to do with the operation? So typically the scale of these things get bigger, but as we mentioned at the beginning, as you get data, you can then start to bring the cost down and refine more and more and more. So, but we are working on low-cost, very low-cost monitoring solutions. But you can go too sparse, where it becomes ambiguous and it can be dangerous. So there is a balance between the two, and I think we have to find out what that balance is for these types of stores.
So actually I have a question and a comment. Hein Vergent, State Supervision of Mines. Thanks very much, Chris. I really liked your start with, you know, very often as a regulator we get the question, what should we monitor? I always turn that question around and say, what do you think you should monitor? And having a very clear understanding of your risks is very, very important. So we need to look back at incidents with regards to that. Not only when it comes to storage in porous media, but also when it comes to salt caverns. And to respond a little bit to what Arnaud was saying, yes, we have had storage for a very long time, which was all allowed with relatively low margins. However, we have had incidents in the past. There were some examples of blowouts. We were hearing about hydrofracts. I will show some examples of that in my own session. And we need to learn from that. And risks are changing, and also regulatory requirements are changing. And the surrounding is, people want more. The backyard is changing. People are more conscious of safety. So thanks a lot for that. My question is related to the microseismicity that you showed, and particularly microseismicity when it comes to salt caverns. So in the Netherlands, we have measuring microseismicity is relatively cheap, and we have a few stations monitoring seismicity in cavern fields in the Netherlands, and we do see microseismicity in the order of 20 events a month in the, with magnitudes below, generally below 0. But we can monitor them. My question to you is, what is your intention when it comes to cavern storage to look at this?
We haven't done too much specific on that at the moment, but it is on the list to look at. The concern, of course, is probably largely the cap rock of the cavern. But also, as we've noted, there are many things within the salt that could also be potential sources of earthquake. So, large shear zones, for example, we do see this in salt domes in the US, for example, large encased pieces of sediment, which could also potentially fracture and release seismic energy. So, I think, like everything, it would be a case of designing an appropriate monitoring array for that type of scenario. But again, it's on a case-by-case basis, largely. But some of the simulations we're showing you from the elastic forward modeling, the surface seismic, we're also performing for microseismic for these types of scenarios as well, to understand what level of monitoring and detectability we might be able to see. So, too early to give you a definitive answer on that, I'm afraid, but it is certainly on our program to investigate.
Naomi started her PhD. Where are you, Naomi? She's going to work on it for 4 years on microseismicity.
Okay, we need to talk.
Next year you will have a poster, hopefully.
Maybe to further stimulate the discussion and to connect it to the first question, should we do more monitoring on salt? We saw during the first presentation as well that one possible concern can be a formation of a new fault due to cyclic injection and extraction of hydrogen. Also, for microseismicity connection to that, existing faults. Do we know all the existing faults there? Have we seen them? And can we see them? Can we see formation of new ones? What do you think, Chris?
Yeah, great. It's a great point. And I think again, we have to go back to obviously the experience where we've had data. And as you know, Shell within the Netherlands, particularly involved with the Groningen gas field. And that just it highlights how things don't go the way that they think they would go. But you bring up a good point about the faults. Many of the faults likely we can't image in the subsurface that are sources of micro earthquakes. But obviously, a lot of the trigger for this is the underlying pressure regime and our relationship with that. So establishing what is the pressure regime within the reservoir before we inject, and then adequately controlling that level of injection over time. It's cause and effect, and that's what we see in each case. I think it's a question.
I think I'm going to also build up on this discussion, because you showed a nice result that you are detecting that seismicity 0.8, something like that. And you mentioned that it's pre-existing faults there, and they are critically stressed. And I wanted to first ask, what was the target pressure that you reached? And of course, you reactivate all those faults. And I wanted to see you had some sort of traffic light system that controlled this,
Yep.
like injection rate, injection protocol, and you can also, let's say, generalize it for the hydrogen as well.
Yeah. In this, typically, with the example of Quest, it's something like, I think, 90% of fracture gradient, the pressure injection into the reservoir. And again, a lot of these are, we come back to the fact that they're site-specific. So in the case of Quest, it's a fairly simple saline aquifer. There is no pressure management like you see at other sites. For example, Gorgon in Australia is a pressure-managed reservoir where water is extracted from the aquifer before CO2 is then actually pumped in. And then the water is then pumped into other levels. So there are very different ways of operating that type of reservoir. But the idea, of course, is not to break the rock. This is not fracking by any means, right? But understanding that initial pressure regime that we're injecting into is absolutely critical. In the microseismic domain, we do build up these traffic light systems where we have a plethora of information that feeds into that to set safe thresholds for the activity. And so far with Quest, that's been very successful. It's been very low level. We've had no concerns or no issues, which is why when you saw in the M&V plan, the M&V plan kind of reduced a bit after 5 years of operation. We had data we could history match with. We could then say which technologies were working really well, which technologies were so superfluous that we didn't need to do further. But they can always be added later if there is any change in the state of the reservoir. So.
Chris, my name is Ming with Halliburton. I want to do a follow-up question regarding the induced seismicity, right? So the question is that when you have a region which is seismically active, what is your approach or what is the thinking in terms of separating between induced seismicity and natural seismicity?
Yeah, great question. That's a tricky one, right? So you're in an area where you're already actively yeah. So yeah, that would be quite difficult, but you'd obviously have to study that regional seismicity for a period of time to understand it. As with microseismic, we're trying to detect and locate and understand the characteristics of the earthquake. It would be the same with any area you would go to. Likely there would be locations may be different, they may be deeper, there may be more regional-based earthquakes that may have different types of focal mechanisms to what you would expect in an injection site type of scenario. So there are potentially differences there that you could actually manage that type of operation in the presence of regional seismicity. But obviously, decoupling the two would be important for the value of microseismicity for your future store in that type of location. So. Yeah, I mean, the array specifically for the monitoring site is going to be very much targeted for the monitoring site, of course. And with all the arrays, what you really need is good offset and azimuth coverage because you really want to locate, you try to triangulate the event essentially. So you've got to really locate well, but that allows you to get good moment tensor inversions of the events that you record, such that we understand what type of energy release that we're seeing, what is the focal mechanism of the earthquake. And many of these have quite characteristic types of focal mechanisms, so it is possible to show that, yes, this is possibly related to the storage operation as opposed to a more regional type of tectonic event. But nevertheless, one would have to record both for a period of time, I think, to decouple the two. Yeah.
So,
Thank you.
Hi, here at the top. The question is really...
Hi, sorry.
Hi, Giovanni Grasselli, University of
Giovanni.
Toronto. So Quest is a really nice project. I was actually I was looking at the plume evolution, and definitely is not symmetrical. But what I was noticing is actually there is a development that is going towards the basement. So because of that, are you anticipating or modeling any increase in seismicity in the basement? Because that is where the earthquakes are happening in that part of Canada.
Yeah, good observation. So what we see at Quest largely are these small events predominantly in the basement below the reservoir. And of course, what's the mechanism for that? Because, and that's something that I've been talking with some of the geomechanicists as well regard to this. So we believe the mechanism is probably pressure diffusion below the reservoir, but mechanically, the basement is significantly stronger than the reservoir itself. So it puzzled me quite a bit why we would see events in a very strong rock underneath the reservoir, and why would you not see that more within the reservoir itself? But the results seem quite definitive. But we should also stress that with all location, and every time we show these things, and every time you see them in publications, there are large errors in location, right? So even though we see that activity appearing below the basement, the actual depth error associated with the position is quite large. And this is a function of the type of array that we're using for monitoring. So here we have very few wells that are acting as monitoring, so it's actually very difficult to get good spatial accuracy for the event locations themselves. But yeah, so far in the basement, the seismic images are not particularly great in the basement, but likely there are faults there that are the source of these events. Yeah. Okay.
You had a question here? Yeah.
Hi. I'm here. I'm David.
Right there.
Yeah. Very interesting conversation. I have a couple of questions which are quite different. But the first one is, have you tried some technique which use inversion, essentially model using microgravity? Because I've seen, I was quite surprised by the diagram you were showing when as soon as you have the increase in the velocity, it means at certain points the density is the only probably way to test it. And I've seen some interesting publication which have been using inversion 4D gravity model on the CO2, basically mapping of the variation of the plume. So do you think it's a direction we could go?
Yeah, indeed. It's something that we're looking at also EM as well, with the resistivity. The traditionally with both the EM methods and the gravity methods has been a resolution one. I think they're good technologies to use in conjunction with, say, the seismic, because often what you want to prevent is the ambiguity in interpretation, because it can suggest maybe something else that's occurring. So yeah, I think for this though, likely downhole, if possible, and there are challenges. Yeah, you know, we have the casing response, for example, in the case of electromagnetics and gravity that need to be overcome. So there are some real challenges in doing the downhole EM and gravity, but I think it has potential. Yeah.
Quick other question. My other question is about the place where you have a lot of earthquake activity. I'm speaking about Italy, where at the moment it's a place where we are storing a lot of gas. Seasonally, because it's part of the security of the country to get gas. And the big problem we have is to create convincing map where we separate essentially natural earthquake in area where you are in constant tectonic stress. So therefore you produce everyday earthquakes. Some of them can be recognized by the focal mechanism. But some other case, the problem is that as soon as you are injecting in some place, there is always the doubt from the people which are controlling the government that some of them can be triggered. Doesn't matter how much they are possible or not. What is your experience in this kind of situation?
Yeah, you have the famous example in Val d'Agri, particularly of microseismicity from wastewater disposal. versus your dam impoundment. So the lowering and the raising of the water in there, and I forgot the major reservoir now, but was essentially inducing micro-earthquakes that I think were initially blamed on the oil and gas companies. But there was a distinct spatial change, variation in that. So why were earthquakes going over here and not actually near the wells where they were disposing water? And it turns out, of course, that it was related to the change in the water of the dam itself. Again, very challenging in an area where you have such seismicity. You have very big earthquakes that release a lot of energy, more tectonic size earthquakes.
Yeah, okay.
Yeah. So I think just when it comes to these stores, typically we're looking at much smaller seismicity on average in a much more localized area. So there should be a cause and effect relation there. And we do see that in places like Groningen, right? It's a gas extraction problem, and that's what happens. Anyway, yeah. Coffee, I hear.
Yeah, Chris. But thanks for the presentation. I really like it. I have a question about relative to underground natural gas storage. The issue on microseismicity, do you think it's going to be different because of the working pressure ranges is going to be different?
Yeah.
The maximum might be lower, and the
Great.
difference between minimum maximum might be larger because of the lower density.
Great question. Something I've been puzzling over myself, whether in the case of a hydrogen store, would we expect to see any differences in microseismicity, for example, due to either the operating pressures of the stores or the natural diffusivity of hydrogen within the reservoir? Would it actually have different rates of earthquake release or not? Could these be actually very quiet types of, don't know, but those are questions that we do need to study as a community. Certainly very interested in that. Yeah.
Chris, hi. Thank you. I thought it was really helpful that you presented your presentation in contrast to CO2. That was very helpful. One thing I have thought about with respect to CO2 and also methane is that if there are leaks, the possibility of satellite imaging to detect leaks is very easy. I know that's not what you talked about, and it's not what you do, but with a molecule that doesn't have a carbon bond, I think hydrogen would not be so detectable. I wonder if you have any thoughts on that, or do you know anything about that?
Yeah, no, great question. Obviously, we don't want any leaks, so all efforts are going into ensuring that we have containment. So the scenario would be, what happens if you did have a leak? Well, certainly for these deeper types of porous reservoirs we're looking at, it would be very difficult to get any of that up to the surface. The only likely way it could probably happen is up the well itself. That's the natural leakage pathway. You put the stuff in there, and that's where it likely would come out. Leaking up a fault over a long area, gradually getting to the surface would be challenging, but we have seen examples, particularly in the US, related to abandoned wells where we have had gas leakage, that a gas plume leaking along, let's say, an aquifer has come into contact with an old abandoned well, and then straight away has shot up to the surface. And I believe there were tragically some fatalities as a result of gas explosion in the near surface. So at the surface side, of course, there is chemical detecting, right? So they will do electromagnetic and gravity surveys for things like the abandoned well locations, but they also go around the neighborhoods looking for methane release. Now that's not hydrogen, but would, and not as a chemist, but would there be any level of concentration that could be detected like that? Unfortunately, with a lot of these abandoned well problems, they've built housing over where these wells are. So people drive around in trucks sniffing for methane, and they've located old abandoned wells under people's houses. I don't know whether something like that can be done for the case of hydrogen or not. You'd probably be able to answer that. Thank you.
Okay, possibly the last question there.
Yeah, I want to put in my 2 cents with regards to the discussion we just had on the seismicity in the basement. I think it was Mark Zobak who was here last year, who gave a presentation about that with respect to water injection, if I remember correctly.
Yeah.
So there is a body of evidence that seems to suggest that indeed changes in the reservoir can lead to microseismicity in the basement.
Yes. Yeah.
But also the discussion with regards to induced versus natural earthquakes. In the Netherlands is relatively easy because we have, a deep basement and shallow operations. But of course things get difficult when the basement and the operational window get closer together and you get something called triggered earthquakes, which are faults which should have moved at some point in the near future anyway, but have been accelerated due to the human activity. And I think as a regulator, I can say that we would tend to side on the side of caution. So it doesn't really matter, to be honest, if it's triggered or induced.
Yeah.
We would just be very, very careful with those kind of activities.
Yeah, good point.
Natural earthquakes are a different thing, of course, which are not related to human activities.
Yes.
Yes, so that brings possibly the discussion back to the beginning, what is cheap and what is expensive. If you save on something, what will happen in the future in the cost, maybe the whole project can be stopped. So microseismicity, what you said, induced or actually triggered artificially, that will require a good monitoring, at least that's what I think. But also to keep in mind, as a message from here, we don't know what will happen, how will happen, how can we get to know that? We need to build extra knowledge. As Chris said, we need to discover new things. Possibly, well, if we don't want to go with 4D seismic, even though it's an excellent thing, well, maybe it's prohibitively expensive. Maybe we should look for other alternative methods for monitoring from the surface. But we need to know also what are the targets, what we need to see, how we want to see it. And that is something that we can take home, or now during the coffee actually, take to the coffee as a discussion. So thank you.